Okay, so we continue. So last time we calculated the Green's function within this Landau's free energy functional, and we calculated G, the correlation function, the Green's function, a 2-point spin-spin correlation function as a function of the distance between any two spins. And we get a bunch of gamma function and spherical Bessel function and so on. So there are two remarks here to be made before we conclude this chapter. So the remaining issue is about the coefficient gamma in this Landau's free energy expansion, this coefficient gamma in front of this gradient eta squared. So that coefficient has a physical interpretation. Okay, so this has the meaning of a range of the interactions. Okay, so for example, in the Ising system, this gamma is actually proportional to this r squared, where r represents the range of this Ising coupling. So there are two ways to actually get the relation between this coefficient gamma and the range of interaction. So the first way is to calculate, again, the correlation lengths near the transition, both below and above Tc. So we know very well that this has this two form, and they differ by simply just a factor of 2 in the denominator, right? And this correlation length diverges as t to the minus 1/2, okay, near the transition. But let's look at the t above Tc, and we can actually factorize this prefactor, gamma divided by, say, 2a with a square root, and we could separate this prefactor from the t dependence, t to the minus 1/2. And we call this Xi of 1. Okay? This refers to the correlation length extrapolated within the mean field theory to temperature being twice as large as Tc. Because you know that this Xi of 1 is precisely this prefactor square root of gamma divided by 2a when little t is actually 1. Little t is actually what? T minus Tc divided by Tc. So when temperature is 2 times Tc, this little t is actually 1. Okay? So then we could simply just rewrite this prefactor square root of the gamma divided by 2a as Xi of 1. But the Xi of 1 has a physical interpretation, which means the range of the interaction correlation well away from the critical temperature. And this actually completes the circle that if we relate these two, we get gamma is actually proportional to square of the Xi1. But we know that Xi1 is actually the range of your interactions, or the range of the correlations at t equals to 2 times Tc. And this is the first way to show that this gamma has a meaning, which is the square of your interaction strength. Okay, the second way to show this relation is by calculating the Gibbs free energy of an Ising model concerning just this Ising term, this Jij term. Imagine that we could consider a simple, this Jij is simply just a constant within this range of interaction and 0 otherwise. So then we could simply just rewrite or estimate this Jij term from that simple assumption. So we could separate this MIMJ term into two terms, subtract from one another. So the first term is nothing but the gradient term, right? So this is the magnetization shifted by delta vector relative to the any position I. And you subtract this to all the parameters at different, slightly different locations, the sum over all possible delta within such a range of interaction. And you divided this by a, and you square this. But this has to be subtracted by the other term, which is the average of these two magnetization. And if you subtract this two term from that term, and you get back to the original MINJ term. So you could simply separate this term into a square difference between these two terms. So then you could simply just estimate these two terms, and very well that the leading contributions come from the gradient term, which carries energy penalty minimizes the difference between adjacent Bloch spin values. But the remaining term is actually all over m squared, which is simply just some kind of a background average term that we don't care at the moment. Okay? So we would like to collect term which is proportional to the gradient m squared, okay, which is the first term. And when we do so, we integrate over the entire range of interaction, and we get to that value here. And we call this prefactor in front of the gradient m squared precisely the coefficient gamma over there. So gamma in this estimation is proportional to r squared times some prefactor. And here the Jz in the Ising model is actually equal to kbTc. From this kind of a simple estimation that the gamma in front of this gradient square term has the physical interpretation of the square of the range of interaction. So with that final remark, we can conclude this chapter. And after a short break, we will start a new chapter, which is about the breakdown of the Landau theory and the Ginzburg criterion near the transition. So let's start by looking at the Landau theory again, especially the mean field part of the treatment. Right? So, for example, the Ising term Jij, Si.Sj, within the Landau theory, remember that we use a Weiss mean field to actually replace this one of the spin operator Si or Sj by its mean value. Here, the average Sj, but we sort of neglect the fluctuations, which is the deviation of this Sj from its mean value. So in other words, we simply just treat this J term, this Ising coupling term, from this mean field kind of approach by replacing one of this Si or Sj by its mean value. And but we know that they are not exactly the same, because this Si average is not the same as Si, because Si should certainly contain fluctuations or deviation from its mean value. Okay, so Si average simply means that we take ensemble average. Okay, but of course, the spin on every side is not just its ensemble average. But in a way that we forget about this, we neglect these fluctuations away from this mean field. Or the other term, so if we take this Si.Sj, Si.Sj, taking ensemble average, and we sort of assuming that this is the same as the product of this each individual ensemble average of the spin. But of course, this is not the same. Okay? But what is the error then? If we simply naively take this mean field approach, then of course we need to estimate the error bar, or the percentage of error, by doing this mean field treatment. And of course, this mean field approach can be rigorous as long as this fluctuated error or error bar is small. So we define this kind of a error bar, this mean field, the Landau's mean field approach, by this ratio. Okay, so the first in the numerator is kind of a deviation of this Si.Sj average from this product of this Si average times Sj average. That is the error by treating this Si.Sj average as each individual separate product of this Si average times Sj average. But this is just the absolute value of these errors, but we need to take the ratio of this value to the Si average times Sj average to get this error percentage of error. So the question is, how large or how small this Eij is it really small? Of course, it's not small in general, but it can be small. So then we need to come up with some kind of estimations, more accurate estimations of this Eij. So we could simply just use our notation that we introduced earlier, that suppose that within this interaction range or within this cluster of spins, this magnetization is actually m, which is some sort of a function of this distance between I and j, which we call this r. And The numerator here is nothing but the correlation function Gij, remember. So this is nothing but the correlation function Gij. But again, in the translational invariant system, this Gij depends on the relative distance between I and j, which is what I call this G of r. So then this error bar is nothing but G of r divided by m squared, because we assume that the magnetization is actually uniform across the lattice. So this m is just some kind of uniform parameter. So then this criterion that this Landau's mean field approach is rigorous becomes the following. When this ER is very small, then of course the Landau theory is self-consistent, but if this is big, then this is not consistent. So we will calculate this E of r in just a moment and find that this value is actually small in certain conditions, but it can be big or large when the system is very close to Tc, or when the dimensionality is actually below so-called upper critical dimension. So let's just try to more accurately estimate this ER, or we call this ELG, Landau-Ginzburg, and we will actually calculate this ELG both away from the Tc and also very close to Tc. We could actually derive the criterion, which we call the Ginzburg criterion, precisely this criterion over here, what this means. Okay, so we will explicitly calculate this criterion so that under such a criterion, this Landau's mean field theory is okay or it fails. So before we calculate this Ginzburg criterion in a very general case, let's just calculate two limits of this kind of error bar that we defined previously. So the first limit is when the fluctuations away from Tc, where the temperature is well below Tc in the order, deep inside the ordered phase. So remember this correlation function G of r that we already obtained previously in that regime takes this form, depending on your dimensionality. And when temperature is well below Tc, this correlation length is roughly the same as the range of interaction r that we already mentioned. And the magnetization in the ordered regime is a kind of a saturated value of order 1 as well. So then you simply take the ratio between G of r and m squared and calculate the error bar ER, and we get this prefactor G, little g here, coming from this correlation function, multiplied by a factor which is order 1, which comes from this fact that this magnetization is actually of order 1 quantity, and also little f function as a function of a dimensionless quantity rho, which is the ratio between this capital R and C, which is again order 1 quantity. So then this error bar is already determined from this little g factor. This g factor depends on this temperature and the correlation length in that way. So then you could simply just plug in this correlation length and here as an interaction range, and you simply just plug in all these prefactors, say gamma, which we just calculated a moment ago, and this is the order of T over Tc times this little a divided by this range of interaction capital R to the power of d. Therefore, it is proportional to this 1 over z, where z is simply just the number of coordinator or number of the neighbors, or the size of the interaction range relative to the lattice constant. So this factor z actually determines whether this error bar is small or large. So if the ratio capital R divided by the little a is large, or z is large, much larger than 1, then this quantity is actually very small. So then this actually tells us that if we have a longer interaction range relative to the lattice constant, then more or less the fluctuations is actually small. So then this mean field theory is fine. And that is good news that this mean field theory is still used for, but it is used for only when the temperature is, say, well below Tc or in the ordered phase. The mean field theory actually works very well, but let's look at these fluctuations very close to Tc, see what happens. In that regime, we know very well that the correlation length diverges, right? Goes to infinity, so it actually goes beyond the range of interaction, capital R. So this dimensionless quantity rho becomes 0 because this capital R is much less than this correlation length, which diverges. And we know that when temperature is close to Tc minus, which is very close to Tc below, from temperature below Tc, and magnetization actually vanishes in the power law of T with the exponent beta. And we simply just plug in this asymptotic behavior of this correlation function and the magnetization, and we get 1 over t, little t to the power of 2 beta. And we know that beta is what? Beta is 1/2 for the Ising mean field theory, and therefore when the little t goes to 0 or temperature close to Tc, and this error bar diverges. You see, in one case the error bar is small and well controlled deep inside the ordered phase, but on the other hand, when the temperature is very close to Tc, the error bar diverges. So these formulas are the estimations of this correlation function near Tc and also the gamma prefactor. So then we get the correct physical behaviors when the system either close or away from Tc. But unfortunately, the temperature range, which is very close to Tc, is the range of our interest, mostly. So we are interested in the behavior when temperature is close to critical temperature. And in that regime, the Landau theory breaks down. So we need to fix this. But first of all, we need to calculate how bad the situation is when this Landau theory breaks down. So to do so, we need to calculate more rigorously the Ginzburg criterion, and we should take the numerator and the denominator, some kind of a volume average, where this volume should be approximately the correlation length volume, which is made of the correlation length in the d-dimensional space. So which is say that all this correlation function magnetization actually are well defined within such a correlation length. So we need to actually calculate this spatial average over those quantities within this correlation volume. So from Landau theory, we know that this integral over spatial coordinate r of this correlation function, capital G of r, is nothing but kBTc times this isosomal susceptibility chi of t that we already calculated some time ago, which is given by some prefactor divided by this little t. So that's the numerator. What about denominator? Well, denominator is very simple and straightforward because this m, when the system is close to Tc, within this Landau's mean field theory, takes the value of the square root of a, where a is the prefactor, is the Landau's free energy expansion, and the absolute value of the little t divided by this coefficient b. So you simply just plug in this, which is some sort of taken as a uniform value over the spatial coordinate. So we simply just, when taking this spatial average, we simply just consider this as just a constant, and you need to multiply by this correlation volume. So let's take a short break. Let's combine everything together that we just obtained for the error bar or the fluctuations within the Landau theory, that the numerator and the denominator have been calculated or estimated separately. And so this is, for example, this will be the numerator, and this will be the 1 over denominator. So 1 over denominator. So we simply just combine all these factors and in a more elegant way, so that we have a prefactor kb divided by 4 times so-called delta c, where delta c is the kind of a specific heat jump at the transition, which is defined by this a squared divided by b times Tc from the Landau's mean field theory. Also, there's this c of 1 to the power of d factor here in the denominator. But another factor depends on this reduced temperature, little t to the power of d minus 4 divided by 2. So that is very important, relation here. So in general, we would like this Landau theory to work if this error bar is very small or negligible. So in that case, we need to actually establish the inequality based on this result over there. So therefore, this little t to the power of this d4 minus d divided by 2 must be larger than that constant we define there. So this has to be much less than 1 in order to make the mean field theory valid. Okay, so then we could simply just rearrange this inequality to that form. But this prefactor, or this constant factor here, we could define this as another important quantity. We call this little t Ginzburg-Landau onset of the critical region. So this has the same dimensionality as this little t as a reduced temperature, but this reduced temperature is actually a constant value, which doesn't depend on this temperature, but effectively this plays the role as effective reduced temperature. Because if you can actually compare this two quantity there, you can easily see that when this little t is larger than this criterion or onset of the critical region, then this error bar is actually small. So mean field theory is okay. But if, on the other hand, this little t is too small compared to this t Ginzburg-Landau, then the error bar is large, and mean field theory fails. So in other words, the TLG marks the onset of a critical region. So any temperature in reduced sense is actually, suppose this little t is actually below this onset of a critical region, then this Ginzburg criterion fails and mean field theory also fails. Which means that, remember, we have this kind of a phase diagram. In the beginning of our class, this is temperature and this some kind of control parameter, and we have a long-range order phase, and this crossover order temperature vanishes at a critical parameter called GC, and at the finite temperature, we have a transition going vertically like this, crossing this red curve at the border of a order-disorder transition. So now we could formally go back to this diagram and formally define this dashed line. This dashed line is nothing but the onset of a critical region. Okay, so any temperature that within this two dashed curves belongs to the critical region. So within that region, this little t is actually less than this t Ginzburg-Landau. So, and therefore, the shape of this little t is actually equal to this t Ginzburg-Landau defines this critical region, or this two cross dashed line there. So, in other words, if we are inside this critical region, then this Landau mean field theory fails, and we need to fix this kind of divergent fluctuations by going beyond this mean field theory. However, if we are away from this critical region and we are safe, especially if we are deeply inside this ordered phase, then this mean field theory works well, because now we are satisfying the other constraint or another condition that this little t is actually larger than this t Ginzburg-Landau, which means that usually if we are in the deep inside the ordered phase, then this criterion is satisfied, then the mean field theory works well. Okay, so when you look at this t Ginzburg-Landau, you need to also think of this phase diagram. Here, you should actually link these two. So this little t Ginzburg-Landau is nothing but this dashed line in the phase diagram. So within these two dashed curves, we need to do something to fix this, the failure of this Landau's mean field theory, but deep inside this ordered phase, we're fine. And so that's, that really emphasizes the importance of this little t Ginzburg-Landau, which is that value over there with some power dependence. And again, so this factor depends on this delta C, the heat capacity jump at the transition, also the range of interaction. But it also depends on dimensionality, little d here. because if you look at this form, so if this dimensionality d is actually less than 4, then this power law is actually divergent, right? As t goes 0, and this t to the power of that negative power leads to divergence of this arrow bar. So which means that as t goes 0, this arrow bar is always divergent when dimensionality is less than 4. However, if the dimensionality is actually larger than 4, then as t goes 0, as we get closer and closer to the critical temperature, then this Ginzburg criterion is always satisfied, or the mean field theory is always working properly. So then it also depends on this dimensionality, this Ginzburg criterion. And this 4 takes a special meaning because it marks the dimensionality below which this mean field theory fails and above which the mean field theory works. So it is called the upper critical dimension. Okay, so we will come back to this later to explain what it means in the context of renormalization group analysis. So exactly when d is actually 4, we call the critical dimension. Quantities acquire logarithmic correction. For example, the chi t acquire this logarithmic corrections near the transition, but we don't have time to discuss the critical dimension. But of course, in the classical system, the dimensionality is always below 4. For example, either 3-dimensional or 2-dimensional or 1-dimensional system. Okay. However, in the quantum mechanical system, in the quantum many-body system, where we may have quantum critical point or quantum phase transition, then the upper critical dimension can be greater than 3. So the effective dimensionality in the context of a quantum phase transition is actually d plus z, where z is not the coordination number but the so-called dynamical exponent, where in the renormalization group context it tells us what is the effective dimension when we rescale the time domain. But the spatial dimension is also within the 3-dimensional space. So d and z could be anything, say, from 1, 2, 3, or to a fractional value, and therefore d plus z can go beyond the upper critical dimension 4. Okay? Again, so we will come back to that later. So let's talk about the size of a critical region. So again, we could actually go that statement there, that when this little t reaches the critical region, which we call this little t Ginzburg Landau, things change. We don't rely on this Landau's mean field theory. So let me just make some comments or remark regarding the Ginzburg criterion. So again, for dimension below 4, where the Ginzburg criterion is always broken or the mean field theory always fails, then the quadratic term in the Ginzburg Landau expansion, remember this Landau's free energy as eta squared plus gradient eta squared and plus this quadratic term, proportional to eta to the power 4. And this term becomes increasingly important as the little t goes 0, where the temperature approaches to critical temperature, because then you know that the Landau's mean field theory fails, and its next term is going to be very important, which is the quadratic term. However, with dimension below the upper critical dimension 4, then the mean field theory works well, so we don't care about this quadratic term anymore. So the Landau's free energy can be just studied up to just quadratic term eta. Okay, so that's the first remark. The second remark is that in general, this critical exponent gamma, beta, and nu can take different values from these exponents predicted in the Ising model. So, for example, gamma may not be 1, and beta may not be 1/2, and this correlation length exponent nu may not be 1/2. In that case, we need to recalculate this Ginzburg criterion one more time by faithfully plugging the general power law exponent near this critical point. Okay? So for example, the numerator in this Ginzburg criterion over there, which is the spatial average over this correlation function, now behaves as t to the minus gamma. And the denominator over there shows t to the power of 2 beta minus nu d as t goes to 0. So when we combine these two, or take the ratio and to actually check or write down the Ginzburg criterion in a more general case other than Ising model, then you come up with this inequality there. So Landau theory is valid if this left-hand side quantity is actually much smaller than the right-hand side quantity. Okay? So if you plug in this power law dependence in the numerator and denominator for a general case, then you could easily derive such a relation that t to the power of minus gamma should be much less than this t to the power of 2 beta minus nu d. So if you simply just compare the exponents and you get the new or general upper critical dimension when its dimensionality is actually larger than this 2 beta plus gamma divided by gamma, then your mean field theory is okay. If not, then it fails. Okay? So you can check for the Ising model where this upper critical dimension is actually 4. So beta is 1/2. So 2 times 1/2 is actually 1. Gamma is 1. So 2 times 1/2 plus 1 divided by 1/2, which is 4. Yes. Okay, so let me just summarize the key points of today's lecture. So in order to estimate the fluctuations within this Landau theory that are neglected, and we formulated this Ginzburg criterion, which is the percentage error within this Landau mean field theory, by neglecting these fluctuations away from this mean field values. And we figured that out that for the Ising model, there is upper critical dimension above which this arrow is actually small, but below which the arrow is actually divergent as temperature reaches the critical temperature. And we also estimate the range of this critical region, which is defined by this quantity over there. And if this little t reduced temperature is less than that Ginzburg reduced temperature, then a mean field theory fails. If we are away from this critical region, then the mean field theory is okay. It's not yet done. Next time, we will continue analyzing this Ginzburg criterion and to actually understand better prefactor there, or this critical region. And also we could study some non-examples in the superconductors, thin film, or other materials with finite temperature phase transitions regarding this Ginzburg criterion and also the critical region. And then we should estimate this kind of critical region from this functional integration point of view. Okay, I'll see you on Thursday. If you have questions, please let me know.